Now this is a Cepheid variable star, which is actually a category of stars which change their brightness over some specific period of time. But here's an interesting thing about this category, which is that if you know this period or the time in which it changes its brightness, you can calculate the star's distance about how far away it is from us out there in the space, even if it is in a different galaxy. In fact, that's how we confirm the existence of galaxies in the first place. Now, with all those stars out there in the space, there are a few which change their brightness over some specific period of time. Now, these might change their brightness in a regular fashion with a fixed interval, or they might be more irregular depending on different things. Now, this change in brightness might be something internal, which is inside the star's body, some change happening inside it. Or it might be something which is totally different, outside in the space, which might be obstructing our view, like some dust passing in between. Now you might think that these kind of stars are rare, but they aren't, because our Sun is itself a variable star, which changes brightness by 0.1% over an 11-year solar cycle. These Cepheid variable stars are just another category of these variable stars, but they are quite special because we can calculate the star's distance just by knowing the period of change in brightness. In fact, they're so good that they serve us as a benchmark for scaling galactic and intergalactic distances, and they also serve us as the standard candles in astronomy. This was one of the most important discoveries in the history of astronomy because it enabled us to calculate distances which were in the order of millions of light years, which was only limited to about few hundred light years from the previous method, which was the method of parallax. Now, with the Cepheid variables, we could calculate the distances of different galaxies. And this was something revolutionary, something which we couldn't do till 1908. Now, a typical Cepheid variable graph should look something like this, which is the graph of its brightness with time. Now we can see that there's a sudden spike in the brightness and sudden increase right here, and then a slightly slower drop in brightness over this period of time. Now this period of change in brightness for a specific star is actually fixed, and it is actually different for different kind of Cepheids. The story of Cepheid variables actually began with the discovery of the Delta Cephei, which was the first Cepheid variable to be discovered, and which is why it is named after the Cepheid variables. Now, with that, as the years passed by, it was actually in the year 1908 that this happened. Now, in the year 1908, there was a group which was working at the Harvard College Observatory under the astronomer Edward Charles Pickering. Now, it was a group of women who were working as the human computers, and they analyzed the photographic plates of the different stars. Now, one of them was actually the scientist Henrietta Leavitt, and she catalogued about 1,777 variable stars. Now, at that time, women weren't allowed to use the telescopes, so they only handled the photographic plates. Now, she noticed a simple relationship between these variable stars, that the variable stars which are brighter also tend to have a longer period. The simple problem is that if we know the star's brightness, we can't really tell how far away the star is. We really can't say anything about its distance. For example, if a star is bright and it might be further away from us, it would appear dim to us. And same is true for a star which might be dim in actual, but is just simply closer to us. They would all be of the similar brightness. So we really can't see anything about it. What we need is the luminosity, which is actually the energy output of the star from its surface. Now, once we get our hands on the luminosity of a star, we can just simply note down how this luminosity fades away with the distance, and just by knowing the distance, we just have a simple relationship with its luminosity. But getting the value of the star's luminosity is the hard part itself, because sitting millions of light years away, you really don't have anything you can do physically to measure about how much energy the star is giving out. Well, this is where the Cepheid variable method comes in, because once you get the luminosity, you already have the distance. And this is where the Cepheid variable star's graph of luminosity versus period comes in, because now you have a relationship with something else, which is the period of Cepheids. So if you have a star and you know its period, then you can get the hands on the luminosity and thus the distance. And this is the reason why Henrietta actually used the stars in the Magellanic Cloud, because they were so far away, and since they were in the same cloud or the nebula thought at that time, that we can take them to be at the same distance. And if two stars would be at the same distance, then the luminosity would actually be directly proportional to the brightness. If the two stars which are at the same distance and one of them is brighter, this should definitely be more luminous. And that's how she cataloged different variable stars and got a pattern of the star's period and its luminosity. And this led to many groundbreaking discoveries eventually. Edwin Hubble calculated the distances of different variable stars in the Andromeda galaxy. At that time it was thought as the Andromeda Nebula. And then he found out that these stars and these Cepheid variables are actually not the part of the Milky Way, which they were thought at that time. And this settled the great debate, whether the Milky Way represented the entire universe or it was merely just one of the other galaxies. And it transformed our understanding, because before, with the method of parallax, we could only calculate the distances till few hundred light years, and which means that if some star is further away than that, you really can't draw any conclusions about it. And once we got our hands on this Cepheid variable method, we calculated distances and really found out that things, how far away they really were. For example, the nebulas and all these galaxies, which at that time were thought to be as the nebulas, were just galaxies which were millions of light years away. Eventually, in the year 1929, Edwin Hubble formulated the Hubble's law with other scientists and showed us that the universe was expanding. Again, confirming with the Cepheid variable distances. So now the calculating the star's distance was simplified. Now you look at a galaxy far away from us and then just observe some of the variables in it, and then if you know the variable, you note down its period, and once you get the period, you just plug it into the graph, know its luminosity, and then you have the distance, which is pretty simple. Cepheid variables aren't that restrictive. There are actually two categories of Cepheid variable stars. The first one is the classical Cepheids, and the second one is the type 2 Cepheid. Now both of them do have some kind of distinct properties. For example, the classical Cepheids are the Cepheids which have very regular periods of pulsations with the order of days to months, about 4 to 20 times more massive than the Sun, and up to 100,000 times more luminous. They're actually bright yellow giants and supergiants of the spectral class F6 to K2. Now type 2 Cepheids are the Cepheids which have a period of variability ranging from about 1 to about 50 days. And they are generally the low mass objects. They are also further classified into subgroups. Well, there is still a question that why do the Cepheids change their brightness? Well, it must be something internally going on inside the star, because the pattern is actually so regular. So it is actually, the popular explanation for this is actually thought to be the kappa mechanism or the Eddington wall. It is actually related to the helium atoms inside the star. Now not only there is a change in the star's brightness, but there is also a change in the star's radii and its temperature. Now the helium is thought to be the most active in this process, and this is because helium is actually just a byproduct of the hydrogen fusion which happens inside a star's core. And what is the case here is that the helium atoms can be found in two states of ionizations depending on the temperatures inside the star, and the ionizations are actually of the different opacity. What it means is that the hydrogen, which is doubly ionized and lost two of both of its electrons, is actually the one which is more opaque. It doesn't let the light pass through it. And then the other ionization, which is the singly ionized helium and has lost one of its electrons, is actually more transparent. So what this means is that if there is more doubly ionized helium, the star would dim in the brightness. And if there's a more singly ionized helium, then the star would be more transparent. Now, the more heated the helium is, the more ionized it becomes. So the dimmest part of the cycle is actually the one which has the more doubly ionized helium. And in the outer layers, because of this, the radiations really cannot escape the star, and because there is a high temperature, the star actually begins to expand. And under this expansion, you see the star cools down and the helium actually becomes less ionized and more transparent, which means that the radiation is now released and we can see the brighter part of the Cepheid cycle. And now, because of the gravitational pull of the star again begins to contract and the whole cycle repeats itself, thus leading to the change in brightness with time as we observe. So that is it for this one, and I hope you guys liked the video. I'll see you guys in the next one. Till then, happy stargazing, and I'll see you later. Bye.